So here's section 5.2, where we apply Newton's second law to uniform circular motion. Two things that we've already seen, but are going to take a chance now to really put them together. Our objectives here are to really remember what are those physical concepts that are surrounding uniform circular motion, and now be able to apply them to Newton's second law and talk about now what we call centripetal forces. We also want to be able to identify centripetal forces that are acting in various situations. Now, first of all, we have to remember that our centripetal accelerations are found by taking the velocity or speed of the object, squaring it, and dividing by the radius of the circular path it's moving through. We are going to use that as we talk through this section. Remember that they are always directed towards the center of the circle, and the centripetal acceleration will always be perpendicular to the velocity of the object. Now, Newton's second law, to recall that piece, says that acceleration is caused by some sort of a net force, by combining all the forces that might be acting on an object and putting them together. Remember, we're going to do this in a various direction. Before we did x and y. Now we might look at forces that are acting radially and forces that are acting tangential to a circle. So those might be our two directions that we focus on. Now, if the centripetal acceleration is directed towards the center of the circle, that means that the net force also is going to be directed towards the center of the circle. It is, in fact, that inward force that actually keeps the particle moving in a circular path. Imagine that we had something that was swinging around in a circle. Maybe it's something that's sitting on a frictionless table, attached to a string, and it's just sort of whirling around in this circle here. Now picture that thing as it turns around the table. According to Newton's first law, the natural tendency of this object is to just keep moving in a straight line at a constant velocity. This is really where the object wants to go at this particular position. But because the string is there, the string is constantly pulling it back towards the center of the circle as it continues to move around in this path, always pulling it back towards the center and always keeping it in that circular motion. It is, in fact, the tension in the string in this particular case that is acting as the centripetal force. Centripetal force is just any force that causes an object to move around in a circular path. It's not any new force. It's really just a new role that the same forces that we've already studied could actually play. Forces like tension, gravity, normal forces, other contact forces. All of these forces have the ability to play the role of a centripetal force. So centripetal force is not its own thing. We would never label something in a diagram as like an F sub c as a centripetal force. Instead, we'd pay attention to what exactly is causing that centripetal force. In this case, it would be a tension force. T would be labeled on the diagram. So as we work through various problems and situations in this chapter, we're going to talk about what particularly is actually acting as a centripetal force. Now, since it is this net force that's actually causing the circular motion, we could say that the sum of these forces can then be set equal to an ma, where the a in this case is of course a centripetal acceleration, causing it to move in a circle. So when we multiply the mass times a sub c is a v squared over r, so really we find that the net force should be equal to an mv squared over r. Again, net force could be from a single force, or maybe it's a combination of forces, but the sum of those forces can now be set equal to an mv squared over r. Let's look at one example here. We have an object of mass half a kilogram that's attached to the end of a cord. So here is our half kilogram mass. Our cord is going to be 1.5 meters long, and this thing is going to be whirled around in a horizontal circle. And the cord is going to be able to withstand a maximum tension of 50 newtons. The question is, how fast can you actually spin this object around in that circle so that you don't actually end up breaking your cord? So again, if we look at the sum of the forces in this problem, we want to set that sum of the forces equal to an ma. Here, we would want to focus on the forces that are acting radially. Anything that's going up and down into the page would simply balance each other out, like a normal force and the weight of the object. The radial forces are really what's actually causing this object to move around in that circle and accelerate. So when we look at those radial forces here. Those radial forces are simply going to be the tension in the line. That's it. It's only this tension force here that actually has the ability to affect the motion of the object, and that would be acting in any sort of a radial direction. So that tension force can now be set equal to an ma, where that a, again, is the centripetal acceleration of a v squared over r. Solving for then the velocity that this thing could move at, we would want to multiply the r over to the other side, and of course divide by m, and then take that square root. If you want to plug these values into your calculator and check your own work, you can pause the video and do that. We know that the maximum tension it can withstand is 50 newtons. We know that the radius of this circle is 1.5 meters. And the mass of the object is half of a newton, or half of a kilogram. When we plug all those values in, we could now solve for our velocity, and you get about 12.2 meters per second as the maximum speed you could spin this thing around at and still have your cord withstand that sort of tension. Let's look at one more example. Here we have a pilot of mass m in a jet aircraft that executes a loop-the-loop maneuver. The aircraft moves in a vertical circle of radius 2.7 kilometers at a constant speed of 225 meters per second. We want to determine the force exerted by the seat on the pilot at the bottom and the top of the loop, and we want to express our answers in terms of the weight mg of the pilot. Let's start with the place where the pilot is at the bottom of the loop. So here's his plane, and our pilot is sitting inside the plane on some sort of a seat, right? Now, if we were to look at the forces that are acting on our pilot at this particular location, of course, the pilot's weight is going to be pulling down. There's mg of the pilot himself, and the seat is also going to provide some sort of a normal force. In this particular case, these are the two forces acting on the pilot, and these are in fact the two forces that we are going to have to analyze as we sum up forces, because they are acting together along the same line of direction. We would call this a radial direction, one going in, one going out, but again, they're both acting together, but they're acting in opposite directions. So when we sum up these forces, we would basically have the normal force pushing up and the weight, mg, pulling down. So we would subtract that mg. Now these two forces in conjunction are now actually creating our centripetal force. That is not always the case where there's only one force acting that creates our centripetal force. Sometimes it might be a combination of forces, just like in this example. Because this combination of forces is causing the pilot to move in a circle, we could set this equal to an ma, where the a is a centripetal acceleration of v squared over r. When we solve this and looking for what is that normal force pushing on the pilot by the seat there, we would essentially write this out as pulling the mg over to the other side and adding these two pieces together. Now, when we look at the way they want this answer expressed, they want the answer expressed in terms of the weight of the pilot, so in terms of mg, which really means that I'm looking to factor an mg out of this expression. If I want to factor an mg out of the expression, I need this term here to actually have an mg. So I really need to multiply the top by a g, and if I do that, I of course need to multiply the bottom by a g as well, so that I'm not actually changing the value of the expression in any way. And now I could rewrite this as pulling out an mg. Here I would simply be left with a 1 once I remove the mg. And here, when I pull out the mg, I'd be left with a v squared over the radius times gravity. Now I would actually be able to plug in my values into the expression in parentheses to solve for some value multiplied by mg. So I'm going to leave the mg outside, and here I would plug in the 225 in for the v and square that. I'd plug in my radius of the 2.7 kilometers, which I'll multiply by 10 to the third, so that I have this value in meters rather than kilometers so that everything is in my SI units. And gravity, of course, is going to be plugged in as a 9.8. When you plug in all those values, you'd find that this entire expression boils down to about 2.91 times mg. What that means is that the pilot is feeling almost 3 times heavier than his normal weight when he's at the bottom of the circle. Let's take a quick look at what would happen if the pilot were instead at the top of the circle rather than at the bottom. We'll find again what his normal force from the seat is going to be exerted, how much that force is going to be. And again, we're going to take a look at that value in terms of his mass mg. So how many times heavier or lighter is he going to feel because he was in this particular location? So now we're still looking at this vertical loop, but this time the plane is at the top of the path. So now the plane's kind of upside down like this. And we have the pilot also in this upside down position. And the seat, again, is kind of here. As we look at the forces that are acting on him now, the forces are going to look just slightly different because here we have the weight of the pilot pulling down, but we also have the normal force from the seat pushing down. So instead of these two things working against each other, where before we had one minus the other, here we see that they're both working in the same direction. So we could instead add the two together, showing that they're working into conjunction. You could call both of them the positive direction if you wanted to. You could call both of them the negative direction, but they do have the exact same sign. So now when we add these two things together and set it equal to ma, where the a is a centripetal acceleration of v squared over r, we now see that this expression changes just slightly. And when we solve for that normal force exerted on the pilot by his seat, we would now have this mv squared over r and subtract the mg. Again, we're going to multiply this by a g over a g so that I can pull an mg out of the expression as a whole and create some sort of a factor of his weight, some sort of a factor times mg. Inside of here, I would be left with my v squared over rg minus 1. And again, I would plug in the exact same values. The velocity is still going to be 225 meters per second. The radius is still going to be the 2,700 meters. Gravity is still 9.8. Go ahead, pause the video, plug those values in for yourself. And you'll find that the factor out front now is about 0.911. So he is in fact feeling just a little bit lighter than his normal weight, a little bit lighter than mg when he is now at the top of this particular loop. Here's just a couple of examples that you're able to see in dealing with uniform circular motion, that circular motion with a constant speed as you maneuver around it. Next time, we'll up this a little bit and take a look at what happens when you're changing that speed, and we'll look at some more examples in class.